welcome everyone to the Northeast Ohio Quantum Computing Meetup. This is our first meetup of 2022, so we're all excited to have you guys here. Just as a recording notice, we will be recording this session. The recordings will be available on our YouTube channel afterwards, and that's where you can find some of our previous recordings as well. All right, just a welcome to everyone again. Just so you guys know, the format and expectations, there will be two 20-minute presentations from our speakers, and they will each have another 10 minutes for questions. Feel free to add questions throughout the presentation in the chat, and I'll make sure to address those at the end of each presentation. Also, thanks to the Cleveland Big Data Meetup for their support. All right. So our agenda for today is going to be a quantum computing level set with John Marksick, and then our guests from Cambridge Quantum Computing / Quantinuum will be presenting TKET, the leading quantum development platform, and they'll be presented by Dr. Mark Jackson. And then Denise Ruffner and Justin Ging from Atom Computing will tell us more about their technologies and leading the next phase of quantum computing. Few announcements that we have. Upcoming, we're planning our next meetup for early summer 2022. There's a few speakers that we are in talks with right now, so we'll send out more details as those are established. Through the Northeast Ohio Quantum Computing Meetup group, we work with Case Western, and they are planning to offer a course on quantum computing next spring semester. And just a general community note, some of the people from the Chicago Quantum Meetup are presenting a quantum computing meetup presentation on ion qubits, I believe. So that will be, I think, at the end of March. So I have the link here. We'll post that in the chat. And if you guys are interested, you can check that out. And then announcements from Cambridge Quantum Computing. We will also post these in the chat. These are the links to their website where you can learn more about their company and some of the exciting things that they're working on. And Atom Quantum Computing has told us that they are hiring for both technical and business roles. So if you're interested, you can post in the chat or reach out to them through LinkedIn. All right, and with that, I'm going to turn it over to John for the quantum computing level set, or Quantum 101 in just 10 minutes.
Welcome, Quantum 101 in 10 minutes. First, what is a quantum computer good for? Around 1994, Shor created the first really large buzz in quantum computing with his algorithm called Shor's algorithm. Shor's algorithm is a quantum computing algorithm that very efficiently factors very large integers. So every integer can be uniquely factored into prime factors, and notoriously this is a very hard problem for like your desktop to do or any classical computer. In fact, the entire cryptography of the internet is kind of based on this idea. The thing that keeps your credit card safe on the internet is the fact that very large integers are hard to factor. Shor's algorithm gives an extreme advantage. If we could ever create a quantum computer that performs Shor's algorithm, we will almost certainly need more secure cryptography for the internet. The second application that there's a lot of hope for is chemistry. So chemistry could be in almost any of its forms, whether it's like drugs or materials science, batteries. There's all kinds of speculations on what this would be good for. We know the basic equations that chemistry follows. Chemistry is made of molecules, and chemical reactions are just reactions between molecules. In particular, the reactions between the electrons, the valence electrons of the system, and the other electrons. But incredibly, the number of computations you have to do to really solve these problems in chemistry is very hard. And the reason it's very hard is because these are quantum mechanical systems where calculations kind of explode exponentially as you add the number of electrons gets larger. So quantum computers are quantum, so they scale in this kind of exponential way that the quantumness of molecules do. And so there's a sort of a mapping from the chemistry onto the quantum computer, and so hopefully it will be very good at solving these types of problems. The last one I wanted to mention is Grover's algorithm. Grover's algorithm isn't quite as large of a speed up. Think about it like a quadratic speed up. What is a quadratic speed up? It's like a square root. So if something took you 10,000 steps, maybe a quantum computer might be able to do it in the square root of 10,000, which would be 100. So it'd be like 100 times speed up. It's not as quite as impressive as Shor's algorithm or chemistry, but it could be enough to still be commercially valuable. Things that get this can potentially get this quadratic speed up are things like optimization problems, whether it's in machine learning or operations research or Monte Carlo methods. Monte Carlo methods are when you model something as a probability distribution and you're trying to take an average or find a percentile or some other statistic by doing sampling. So in Monte Carlo, you do the computer just samples the distribution and it calculates a sample average. For instance, in option pricing, you're looking for an average over the payoffs of your option. In risk management, you might be worried about like a certain percentile, like a 1 in 200 year hurricane or something like that. What is a quantum computer? The smallest part of a quantum computer is a qubit. A qubit is any quantum system, quantum mechanical system, that has two states. In other words, it can be measured to be in one of two states. We usually label those states with a 0 and a 1. And notice that the labeling includes some extra notation, a vertical line and a greater than sign before and after the 0 or before and after the 1. That's to indicate that's a quantum state. So a quantum state isn't exactly a number. We've just labeled these quantum states with numbers. However, if you have a qubit and you measure it in the state you labeled 0, you could output that to a classical computer as a 0. Or if you measure it in the 1 state, you could output the 1. The interesting thing about a qubit, about a quantum mechanical states, is that states can be put into a superposition. So you can be partially in a 0 state and partially in a 1 state. It's important to know you can never observe a state being in a superposition. When you measure the state, it'll either be a 0 or a 1. But when you're not measuring it, you can do operations to the qubit that will put it in a superposition. Basically, it means there's some weighting on the 0 and some weighting on the 1. And these weightings are the probability you'll measure a 0 or the probability you'll measure a 1. If you're in a superposition, you can see in this picture where you see this sphere, if you're between the 0 and the 1, you also get an angle, which is called the phase between the two states in a superposition. There's, for any two states that are in a superposition, there will be a phase, there will be an angle between them, and that's called the phase angle. So you get those two pieces of information. You can't do a whole lot with one qubit, but the goal of quantum computing is to create, say, 100 qubit system or a 300 qubit system or a million qubit system. And this is where you get this exponential scaling. So if you have 2 qubits, you could measure the first state as a 0 and the second state as a 0. That would be the state 0, 0. Or the first one could be 0 and the second one could be 1, 0, 1, or it could be 1, 1, 0 or 1, 1. So there's 4 possible combinations. If you have 3 qubits, as you can see on the slide, there's 8 possibilities of 0s and 1s. So this number of states goes up exponentially. And in the quantum computer, inside of it, when you're not observing it, all of those can be put in superpositions, which means there are probability weightings. There are 2 to the n probability weightings, or to be more precise, 2 to the n minus 1, because it has to add up to 1. But it's something that scales exponentially. And also, if you have a superposition, if you have any of these states in superpositions, they also have these phases between them. That's very important, the phases we'll see later. So it's interesting that you add a qubit. You do more than just add 2 pieces of information, an angle and a probability. You really sort of double the amount of information. So where is all of this other information? It's not in any particular qubit. It's somehow shared amongst them. And that extra information is called entanglement. If you have a state in a superposition where you have this other information, it's called entanglement. And you can observe entanglement through correlations of the measurements of the individual qubits. So if you have a 2-qubit system and there's like a correlation between measuring a 0 and a 0 and a 1 and a 1 versus a 0 and a 1 and a 1 and a 0, then that would be entanglement. And you can see the space grows exponentially, like 2 to the n. Once you get to like 300 qubits, you see on the slide 2 times 10 to the 90, that's going to be bigger than any classical computer will ever be built, because it's more than, say, the number of atoms in the observable universe or something like that. So it's a very large computational space. So we're 28 years from Shor's algorithm, and we have an exponentially large computation space. What are we waiting for? And this is what you've probably heard of catch-22. I like to call this the catch-2 to the 22. It's such a hard problem. It's a very large catch. What are we waiting for? So on this slide, I have 5 items to think about. First is, we want to create very complicated states inside of our quantum computer. But if we had a 100-qubit system, we could not just do one operation on all 100 qubits. We can only do an operation on 1 qubit or 2 qubits at a time. So algorithms have to be written in this gates. And if you have too many gates, of course, you're not going to get an advantage over classical computer. Second is probabilistic. So if you put an algorithm which on a 300 qubit system, and the result is basically like a uniform distribution, and you want to, find one state, you could imagine it's going to take you like 2 to the 300 trials, which is impossible. So, so the algorithmic idea, is to find algorithms that are very complicated, that make very complicated quantum states, but then use these angles these angles we talked about in the superpositions, because these gates are basically going to be adding states together. And if the states have an angle that's close to 0, so these states are in a sense pointing in the same direction or lining up, you'll get constructive interference, in which case they'll be more likely to be the result of measurements. Or if the angle is close to 180, so they'll be opposite, they cancel each other out, it'd be very unlikely to observe them. So the best algorithm is like Shor's algorithm, that very efficiently creates a very complicated state. And then you very likely, when you measure it, you will get the information out of it very quickly without having to take lots of samples. Those algorithms are hard to find. People have worked on it for 30 years, obviously, and it's not obvious sometimes how to do it. The other issues are with the hardware. If you have a very complicated high number of qubit system quantum state, it tends to decohere very quickly or lose coherence. Basically, anytime it interacts with anything in the environment, you lose information. This generally will require you to have some extra code, which is called error correcting code. There are great mathematical theorems that give us lots of hope that these error correcting codes will work and will give us very long lasting information, but they do come with an overhead of hardware and an overhead of software. And finally, it's difficult to scale up the hardware. You can imagine these little qubits, they're quantum mechanical systems, they're very delicate. You have to treat every one of them. You have to entangle lots of them, and they might be physically very far away from each other as you scale up. So it's very hard. That's Quantum 101 in 10 minutes.
All right, thank you, John. Up next, we have Dr. Mark Jackson from Cambridge Quantum Computing / Quantinuum is going to be presenting TKET, the leading quantum development platform. And just to briefly introduce Dr. Mark Jackson, he received his Bachelor of Science in Physics and Mathematics from Duke University and a PhD in Theoretical Physics from Columbia University, then spent 10 years researching superstring theory and cosmology, co-authoring almost 40 technical articles. To promote the public understanding of science, he founded the science crowdfunding platform Fiat Physica and nonprofit science partnership fund. He is adjunct faculty at Singularity University and a director of Astronomers Without Borders. All right, with that, Mark, I think I'm going to have you take over the screen share.
Thank you so much, Austin. And it's great to be here. and speak with you all. Thank you also, especially John, for that fantastic introduction. In fact, it touches upon many of the points that are relevant to the presentation I'm going to give. So thank you for doing that. And let me share my screen here. And I think you can all see that now.
Yep, looks good.
So I am the Quantum Evangelist at Quantinuum, which, as was mentioned, this is the recent merger between Cambridge Quantum, which was a quantum software company, and Honeywell Quantum Solutions, which was a quantum hardware company. And so in this presentation, I will sometimes use those names interchangeably. We've actually kept the Cambridge Quantum name for now, just for branding some of the software that we've developed. So the amazing thing is that we have actual quantum computers right now. John talked about some of the motivations for why we want to build these, but the amazing thing is, after decades of research, we really have functioning quantum computers. And what's more, there are several different ways to accomplish this. The first, we're using superconducting technology, and this was used by IBM and Google and Rigetti. And there's now effort in ion trap technology, and this is an approach used by ourselves at Quantinuum, as well as Ion Q and a few other groups. There's photonic, and then there's various other approaches which are being researched. And so it's not obvious which is the best technology. There will probably be several winners because each has their own advantage and disadvantage. It is not just the number of qubits that's important. As John mentioned, every time you have a qubit, you're doubling the number of configurations that you can consider at the same time. But in the real world, qubits aren't perfect. They have an error rate, and they only have a finite coherence time, or the time that they keep their special quantum properties. And so to take all of this into account, IBM popularized this term called the quantum volume, which it's a complicated formula, but it's one single metric that can be used to estimate the power of a quantum computer. And you can also use it to compare different quantum computers of different technologies. The progress in the past few years has really been extraordinary. I think many of you are familiar with Moore's law, which has shown over several decades that classical computers have doubled in power every 18 months or so. But quantum is on a much faster trajectory. So just by IBM, so that's the purple line there, they've been able to double the quantum volume every 12 months. And even more than that, Honeywell, which is now Quantinuum, they have increased it by a factor of 10 every 12 months. And so in the next few years, if you extrapolate that just in a few years, we're going to see some very powerful quantum computers. And that's why we think that we're only 3 to 5 years away from commercial advantage. And that's why companies who are going to be benefiting most from quantum computing have already started investing in this. Right now, of course, we don't have these quantum computers of our dreams. We have what are called NISQ quantum computers, and NISQ stands for Noisy Intermediate Scale Quantum. So this means we have 100-ish qubits at most, and sometimes less than that, depending on the technology. But we still get a very high quantum volume because of the relatively low error rate. But overall, the error rates are still relatively high. We still have relatively low coherence time. We can't yet do quantum error correction for the entire circuit. And we still sometimes have problems with connectivity in that one qubit is only connected to a few other neighboring ones. And this is especially true in a superconducting approach. And so for all these reasons, right now, a lot of effort is going into hybrid algorithm development. And so that means that so-called quantum algorithms are actually a mix of quantum and classical, where a lot of the heavy lifting is done still by the classical algorithm, and only some commands, which really benefit from the quantum speedup, are sent to the quantum processor. Now, to get a little more relevant to TKET, I think many of you are probably familiar with a compiler. So a compiler is really just a translator between what we as human programmers type and what the instructions that the machine understands are. And so what we type, of course, is something like C or Python or Fortran or some other language. And the machine just understands switches because it's ones and zeros switching on and off different things on the machine. So a compiler does this translation, and a good compiler not only does this translation, it does it efficiently. So the program runs as quickly as possible, and it uses as little memory as possible. It's exactly the same thing for quantum computers. So this is the stack. This is the order of instructions that is usually followed. in a quantum computer. So at the top of the stack, these are the applications. These are the things that actually solve problems. And this is what you as a user would be doing. And an application depends on different algorithms. So this is the actual code that the programmer writes to solve different mathematical type of problems. And these could be chemistry or machine learning or natural language processing and such. And those algorithms in turn have to talk to a software development platform or compiler. And in this case, that would be TKET. So TKET is the liaison between the quantum algorithms and the hardware or simulator. So TKET is unique in that it is completely universal. You can write your program in any of your favorite quantum programming languages, like IBM's QuizKit or Microsoft's Q# or Google's Cirq. You write your program in any of those, and then you can execute your program on any of these popular platforms that I've listed here on the right. So that includes our own machine at Quantinuum, but it could be any of these others. And all of these details are invisible to you as the user. You simply write your program as you want, and you add one line saying, compile this program and execute it on whatever platform you choose. And that's it. TKET does the rest. So TKET knows all the nuances and details of the language that you've used, and it knows all the details of the architecture in the hardware or simulator that you've used. So TKET will automatically find the most efficient way to run your program on that hardware or simulator. This is a comparison showing TKET compared to several other platforms. And you see that it is by far the most universal. The only notable exceptions are D-Wave, because until recently, they were focused on the annealing approach. Now they actually have pivoted a bit to include gate-based. So soon, TKET will support D-Wave. And then Quantum Circuits Inc., the group that came out of Yale, only because they just haven't written an extension yet. But in principle, it absolutely could. So how does TKET work? How does it do this efficient compilation? So there's two halves to this story. So the first half is TKET optimizing just the circuit itself. This has nothing to do with the hardware. It's just the circuit itself that you've programmed in. The second part is specific to the hardware. And so I'll talk about each of these in turn. So just focusing now on the circuit optimization. So the first part of this is what's called people optimization. And so this means that TKET looks at your quantum circuit, your program, just locally. So it looks at the individual commands and the commands right next to that, and it looks for patterns. And when it finds a pattern that it recognizes and one that it can make an improvement on, it does so. The more macroscopic optimization looks at the broader circuit and it looks for larger patterns. And so then it uses advanced mathematics to try to come up with shortcuts. So let me go through a few examples to illustrate how this works. So this is a typical quantum circuit. So every horizontal line here represents a qubit, and you read this from left to right. So each qubit on the left is getting initialized, and then there are operations happening. So these are putting the qubits in a state of entanglement and superposition, as John explained. And then at the end, the qubit is getting measured. So that's that black measurement box there. And that's forcing the qubit to choose, are you a 0 or are you a 1? So up until then, you don't get to peak. But when you measure it, you're forcing the qubit to choose. And then it becomes a normal binary output. It's either just 0 or 1. So this is a very typical circuit with all these measurements. What TKET does is it goes through your circuit and it looks for different patterns. So this is the people optimization. The simplest type of replacement it can do, it's there on the upper left-hand corner, and that's 2 CNOT operations in a row. And the reason that this can be replaced is because this is mathematically identical to nothing happening. So the 2 CNOT operations cancel each other out, and this is equivalent mathematically to just leaving the qubits untouched. So what TKET does is if it sees this, 2 CNOT operations in a row, it removes them, and this allows your program to run a little bit faster, and it's a little less likely to make an error. These other replacements that I've shown here, these are less obvious, but if you had some time on your hands, you could check that the before and the after are mathematically identical. And this, again, speeds things up and makes your program a little bit less likely to make a mistake. And if you're curious about the underlying mathematics, I've given here the archive article, if you'd like to look up exactly which replacements it does and why. So the second half of TKET's optimization is optimizing for the hardware that you've chosen. And there are several components to this. So the first is just how the qubits are physically touching. So which qubits are connected TKET knows all this again, so it will find the most efficient way to map your circuit into that hardware. The second thing is translating the operations that you've done into the operations which are native to that hardware. And then third, there are issues involving delayed measurements in some cases in hardware that supports this. So let me give some examples to show how important this could be. So these are 3 different superconducting technologies by Google, IBM, and Rigetti, respectively. So you see that even though they're superconducting, so they have something in common, the way that the qubits are connected is very different. And furthermore, the basis gates, so the native operations to that platform, are also very different. And these don't necessarily have anything to do with the gates that you've been using in your circuit. So TKET will automatically adjust your circuit to map into that hardware. So here's an example where this would be very, very important. On the left is IBM's Melbourne machine, which has at most 4 qubit couplings. So that means that at most 1 qubit is connected or coupled to 3 others. And on the right, this is a circuit with some 5 qubit couplings. So you notice those 2 qubits at the bottom, they're coupled to each other as well as each of the 3 on top. Naively, we might think that there's no way to run that circuit on the right on the hardware on the left. That's not true though. We actually can do that. We just have to be clever and we have to use something called routing. So routing means that you're moving the information between 2 qubits around. And this is performed with something called a swap gate, where the information switches places. And this is a perfectly legitimate operation. You can accomplish it using 3 CNOT operations there. But of course, this is what we don't want to do. We don't want to add more operations unless we really have to. So TKET has this built-in optimizer. It will find the most efficient way to map your circuit onto the hardware, and it will do the routing and swapping if necessary. And again, we don't want to do this unless we have to, but TKET will find the most efficient way to do this. Obviously, we use TKET for our own internal algorithm development at Quantinuum, but many other groups have been using it as well. So IBM and Google and CERN have all published articles in which they've used TKET favorably. So I've given the headlines here, and in some cases, it was a very dramatic improvement. And these are some benchmarks done by an independent group named Arlene. On the left, this is the number of operations that they found for different hardwares, and there was always an improvement using TKET. And the graph on the right, this is the execution time, and I want to point out especially that the vertical axis there is on a logarithmic scale. So using TKET was orders of magnitude faster in execution time than using some of the competitors. And especially in this NISQ era, that could mean the difference between having your program run and not run. Because if it takes so long to run, it's just you're going to get a bunch of errors and the result is meaningless. So there's really no point. And so again, especially in this NISQ era, TKET is really essential. We are constantly updating it. And at the end of September, there was a big change. We made it completely open source. So this means not only is it free, every line of code in TKET is now publicly available. You can go through and inspect every aspect of how TKET works. If you have a hardware group, you can write your own extension so that TKET supports it. And if you have some clever idea for some optimization subroutine to make circuits run faster, you're absolutely welcome to contribute to that. And so again, I encourage you to look at it and go through it carefully. We have some big things coming up soon. So one thing we're doing is Kermit, which is an error mitigation toolkit. So again, we're not quite doing error correction, but we can do error mitigation. So there are some tricks that we've figured out on how to reduce the errors. We are also moving it to the cloud. So right now you download it from GitHub and you do the compilation locally on your machine. But soon we will have a version in which you can use it as a software as a service. And there are several advantages to this. So the first is that you will always have the latest version of TKET. It's easier to collaborate and work with other people. And finally, you can use cloud platforms like Azure or AWS to do the compilation. And as circuits get more sophisticated, this will really be essential. Finally, we're already looking beyond NISQ because we know that in a few years, the hardware will be there. We'll be doing things like quantum error correction. And we're already starting to build this into TKET. So we already have a research team focused on this so that when the hardware catches up, TKET will automatically be able to support that. This is how you download it. If you want to take a screenshot for a moment there. So you just go to GitHub, and this is the repo, and there's lots of documentation and examples. There's lots of information to help you get started there. And the installation is completely straightforward. It's the usual pip install for PyTicket. And then you also just need to add whatever module you think you will be using. And so that could be QuizKit or Circ or what have you. And so it's very simple and straightforward to install. So that is it for my prepared remarks, but I'm happy to answer any questions that anyone might have.
All right, thank you, Mark.
On chat, please.
I'm sorry, what was that?
Just if you could kindly put all these links on chat.
Oh, certainly.
Thank you. What kind of error correction do you anticipate, essentially, how it was going to be implemented? Essentially, you do the error correction coding, I mean, on the fly or offline, or how?
When you say what type of error correction?
Yeah, that's one question. And the other is, are you going to do it on the fly or essentially offline and then plug it in?
So there might be a misunderstanding about what quantum error correction means. So when a qubit fails, when it does something it's not supposed to do, normally that would spoil the whole circuit, right? Because that gives you a wrong result and that will change another result. And so what quantum error correction is, it's a way of cleverly smearing the information of one qubit over several qubits so that if one fails, So
my question is, so essentially you're going to incorporate all this error correcting inside.
Correct.
So the circuits will be essentially expanded for error correcting coding. Okay.
Correct. Yeah. And again, you as the user wouldn't have to do that. That would be automatic.
Okay. But do you have a choice of the algorithm of the error correction or not?
Yes. Yes.
Because there's so many.
Yeah, and yes, you're correct. Yeah, there's many ways to accomplish that. Correct.
Oh, that's interesting. I didn't actually know that there were different algorithms that could be used for that.
Yeah, there was the original version developed by Shor. It's very intuitive. You can see exactly why it works, but it requires 9 qubits, 9 physical qubits for every 1 logical qubit. And then people figured out other ways to do it, which use fewer qubits, but they're less intuitive. And so there are different ways to do it depending on how intuitive or compressed it is.
Okay, that's really
So
interesting.
in TKET, you still have to write the quantum code. It looks like it's not like I could just submit an optimization problem somehow or something like that, and it would like write the quantum code.
That's right. That. Yeah, it's still for quantum code. Yeah, so you have to write the quantum code already. This just makes it run as quickly as possible.
Even in classical computing, I mean, you cannot do that either. Too soon for that.
It's interesting to me that you had to solve a routing problem, which you might be able to use a quantum computer for in order to optimize a quantum computing code.
You were not the first to have pointed this out. That's right. Yeah, there is an NP-hard problem that TKET has to solve just to do the compilation. Yes, hopefully one day we could use a quantum computer to do that.
Hey, Mark, good evening. Thanks for your presentation. My name is Pathikrit Mukherjee. Can you hear me?
Yeah, we can hear you.
Very nice to meet you.
Thanks. So I have worked on Q-Skid a little bit. I was trying to get the certification, and while preparing for that, I went through the finance packages and stuff like that, VQE, QAA kind of algorithms, and I actually tried to implement them for certain problem I was dealing with, like currency arbitrage and stuff like that. One of the things that came to my mind is, so you're basically trying to be a bridge between Qiskit and say, for an example, IBM hardware or Google hardware, I mean Circ or AWS or Microsoft Azure, right? Now, yeah. For an example, Qiskit provides lots of packages, finance packages, right? For an example, portfolio optimization is one of the package where I actually worked. So it's already a predefined code over there. If you try to, so when we feed that in the TKET, what is really going to happen? Because you cannot change the underlying algorithm of those packages, right? That is number one question. And number two is, I'll actually come to the number two question later on.
Yeah, maybe let's let him answer the first question.
Yeah.
Sure.
Thanks.
So you are correct. QuizKit is fantastic, and it has many libraries, including financial. What TKET allows you to do is run it in a more efficient way on the machine that you've chosen. And so you can keep all the code that you've written already using QuizKit. You can keep that. Just add one line in the beginning, say, compile this using TKET on such and such machine. And that's it.
So there is a possibility that even though I compile it on top of that, like import, right? Whatever imports that I need to do, it may not find another optimized solution. Is that true? And if that doesn't find it, then but still your TKET is going to help me to run it in any hardware. Does it make sense?
That's right. Yeah, it doesn't change the mathematics of your code. So a quantum program is really just a big matrix which mixes up qubits and everything, right?
Right.
So TKET doesn't change any of that. Your program will be identical, but it will accomplish that same thing using fewer commands, which means it will run faster and it's less likely to make mistakes if qubits fail.
Okay.
So it kind of handles the compiling in the background. Is that what you're saying, Mark? And so the actual code that you put in, I mean, it's going to be the same regardless of what machine or anything. But what this does, what TKET does, from what I'm gathering here, is it handles that behind the scenes of compiling and setting up how the qubit error handling is done in the background.
That's exactly right. Yeah, it's just how the program is sent to the machine. That's what TKET handles.
Okay. And my second question was, while doing those finance packages, I realized one thing, that most of the financial problem in QuizKit, they are trying to first make it to a, it's kind of an equation, primarily quadratic equation. So they're trying to feed that, for an example, portfolio optimization, they're trying to feed that in a quadratic equation. And then they're, putting it either to a VQE algorithm or QoA, and they're trying to minimize the Hamiltonian and stuff. You probably know them much better than me. And when we are trying to find the maximum, the minimum eigenstate, and then it's more of a binary problem actually. So while we are doing all those gizmo stuff, right? What TQE brings on, because again, the question is rotating in my mind in the same way, like if you cannot change the underlying software, and the software is basically translate into the hardware, isn't it? Like all those gates that you've shown, right? They are the backbone of those softwares. So you're saying you cannot change the software. That means you probably would not be touching the hardware. I mean, those gates as well. And this is where I'm a little bit confused, if you don't mind. I mean, I'm trying to understand it a little more. Like, so you're basically working as a wrapper on top of my QuizKit program, which will make it to run fast. But exactly, you're trying to reduce the gates, what you have said, right? If you try to reduce the gate, that means there is a possibility or kind of probability that the underlying, algorithm might change, isn't it? I mean, how do we guarantee that it's not going to change it?
Right. So I understand exactly what you're saying. You're right. So your quantum circuit is a bunch of gates which are there to solve some equations. What TKET does is it finds a more efficient way to do that same thing. So think back to that example I gave with two C0 gates in a row. That is mathematically identical to nothing. The two C0 gates cancel each other out. So removing them doesn't change your program. It just makes it run faster. And so that's what TKET is built around. Mathematically, it is identical to what you wrote originally. It just uses fewer gates to accomplish it.
So,
okay, so sorry, go ahead.
I was just going to ask a kind of a clarifying question on that. So I guess, Mark, is this more about the mapping the algorithm to a qubit, or is this more in the, I guess, kind of that background, just like an efficiency check on the existing algorithm, or is it both?
It's both. So the first part is condensing just your circuit. So mathematically, it's identical. It just uses fewer gates. The second part is mapping your circuit to the hardware.
Okay.
Yeah.
Okay. All right, I'll probably be working on TKET then, if possible, in future, and try to compare like how the results are matching or not. That probably is a good idea.
That would be wonderful. I'm actually putting my email address in the comments there if anyone would like to.
Yeah, just as a just to note to everybody, Mark has put a link to the GitHub, and also
Yeah, I
you can reach out to him. Oh,
So,
awesome.
Mark,
That's exciting.
so kind of like a compiler, you can have a C compiler that runs against, 8086, and a C compiler that runs against, Microsoft 32-bit, 64-bit, and a bunch of other stuff. This is kind of like the compiler part. You're adapting it to the specific hardware, optimizing the specific hardware, right?
Correct. Yes. Yeah. That's exactly the same as with classical ones. It's just that this is for quantum computers.
Mm-hmm. Yeah, and also the fact that you guys have the connections to map up to different different companies' computers and qubits. I guess a question about that would be, what's the difference between, if I wanted to connect with IBM's computers, for instance, what would be a difference between trying to like hook up directly to theirs myself versus using yours? Is like,
sure. So you still need access to the computer. TKET doesn't give you that. So it assumes you have login credentials and everything like that. And,
okay.
And IBM has very generously made a lot of their lower end machines available for free. So that's a good example. So yeah, again, you can use the same login credentials and everything. You can use the same program, just add one line to your code saying use TKET to do the compilation. And everything will work exactly as before.
For installation, it will not interfere with Qiskit. I already have Qiskit, and it will not interfere. It will be
it will not interfere. It will not interfere. Many people use QuizKit and TKET in conjunction.
Yeah, because Qiskit uses its own
That's
Python
awesome.
version, etc. Yeah. Okay.
All right. It is 6:45. Does anybody have any last questions?
And Mark, if you have time to stay on, people might ask him in the chat when we do the next presentation.
Certainly, yeah. I'll be here and answer anything.
Yeah. So in that case, Mark, thank you so much. I think we'll wrap up questions for now, but some really good ones I think that were presented. Mark has also pointed out that you can reach out to him at mark.jackson@cambridgequantum.com. That is in the chat. So with that, thank you so much, Mark. Really appreciate your presentation on this.
Is LinkedIn also? I'm sorry, can we connect? Okay,
Mark, it sounds like they're asking if we can connect with you through LinkedIn.
Yes, yes, of course. Yes.
Okay.
By all means.
Awesome.
That's great. I'll probably send a request then.
All right. Well, thank you so much, Mark. We are going to go ahead and transition to our next speakers from Atom Computing. And I will go ahead and share the screen. Just give me 1 second. All right. Can you guys all see my screen?
Yes.
Okay. So our next presentation is going to be by Denise Ruffner and Justin Ging from Atom Computing. This will be leading the next phase of quantum computing. For the backgrounds, Denise Ruffner is the Chief Business Officer at Atom Computing, a growing startup company building quantum computers out of optically trapped neutral atoms. So one of the other unique technologies that's being used for these qubit technologies. As a Chief Business Officer, Denise is responsible for the company's strategic customer and partner ecosystem and business development engagements. Denise serves as the president of Women in Quantum, a rapidly growing organization dedicated to highlighting and creating a community for women in the quantum field. Denise previously led business development at IonQ, where she was responsible for all customer development and corporate sales strategy worldwide. Prior to that, she was the Chief Business Officer at Cambridge Quantum Computing. Recognized for innovation, sales leadership, and strategic planning, Denise held a variety of leadership roles at IBM, including part of the IBM Systems quantum computing team, where she developed and headed the IBM Q startup program and led the worldwide IBM Quantum Ambassador team. Denise has a master's in neurobiology and molecular biology from the University of Pittsburgh and a Bachelor of Science in Biological Sciences from UC Irvine. Justin Ging is the Chief Product Officer at Atom Computing, where he is working to commercialize highly scalable quantum systems to enable computational breakthroughs for the logistics industry and beyond. Prior to joining, Justin was the Chief Commercial Officer for Honeywell Quantum Solutions, where he led marketing and business development activities. Justin previously led marketing teams at Samsung, Aptina Imaging, and Analog Devices, driving development and adoption of cutting-edge semiconductor products. Justin has also held engineering roles at Bell Labs and Lockheed Martin. Justin holds multiple degrees from MIT, including an MBA, bachelor's and master's degree in electrical engineering and computer science, and a master's degree in material science. And with that, I will hand it over to you guys.
All right, great, thanks. I'm going to bring up our slides here.
Thanks, Austin, and thank you everybody for staying on the call. Appreciate your interest. What we want to do today is to talk to you about Atom Computing, which is a newish company in quantum computing hardware technology. And we'd like to tell you a little bit about our company and why Justin and I, who are veterans, as you can see from the industry, are so excited to be part of this company. So if we go to the next slide. Wow, okay. Can you all see the full slide? Or is that me?
I can see commercial quantum computing is the title, and I see your logo on the bottom as well as the number. Looks like it's the full screen.
Okay, thank you. So in quantum computing, as many of you know, the first quantum computer was a 5-qubit computer that IBM put on the cloud in 2016. And at the time, we thought a couple hundred people would be interested in using it. We had no idea it would achieve the popularity that it did at that time and still does today. Also during that time period, there were a lot of other companies developing quantum hardware, including Rigetti, Honeywell, and IonQ, and also about 10 companies developing software for quantum computers. So this is an industry that started out very small in the 2016 timeframe, and we're now 5 years later. And today, experts expect $1 billion in revenue in 10 years from now. They're thinking that quantum sensing will be one of the first quantum applications to bring significant revenue. This information came out of a conversation that I had with Carl Williams, who's the exiting head of NIST. And it's a fascinating conversation, and I'll tell you later how you can listen to it. But he made some amazing, I thought, very good perspective comments on the industry. So I encourage you to read a little bit more about Carl Williams and learn from him. I thought he was great. On the next slide, I want to talk a little bit about quantum computing hardware because it's confusing. There are a lot of different types of quantum computers, and I love this graphic because what it shows you is the many different types of quantum computers in the inner ring. And in the outer ring, it shows the different companies and the different universities that are developing the technology. And so as you can see, the majority are working on superconducting hardware, but there is a lot of work being done on trapped ion and photonic and quantum dots and neutral atoms. And so I wanted you guys to get an idea of the ecosystem that's going on in terms of computer development. And I would just say that over time, the leading technology may change, it may not change, but there's a lot of work to be done as we move forward in developing this technology. Now, when we look at quantum computers, probably most of us in the industry that are developing hardware look at it as multiple generations of quantum computers. In the early generations that I mentioned, which was the IBM and Google superconducting and the Honeywell and IonQ trapped ion, are what we're calling the early quantum systems. But there is a second generation of quantum systems that are coming. And I think we're going to see a lot from different companies as this year progresses and as we move into the next couple of years. And so some of the technologies that we're going to see include neutral atom. And there are a number of companies working on neutral atom, among which atom computing is one of them, as well as photonic and silicon spin. So I think part of the excitement of the industry is watching all these different modalities and watching how people progress in developing the modalities and really turning them into something that's useful and can bring applications that achieve quantum advantage or exceed classical computing capabilities. Now, atom computing, just to give you a brief background, started in 2018. And our Chief Technical Officer, Ben Bloom, had a background in neutral atom technology, but after grad school and a postdoc, went to work at Rigetti Computing. And after working at Rigetti for a couple of years, he realized that neutral atoms had quite a bit of promise and turned and formed a company along with Jonathan King to work on neutral atom technology. Early in 2018, they got $20 million in funding. And over the past 2 years, they've developed a 100-qubit quantum computer. It's amazing to go to 100 qubits in 2 years. As we know, it took many other modalities longer than that to get to 100 qubits. And it's quite a challenging thing to do, and it's quite a significant achievement. Along the way, we've also shown world record coherence times, which will be very important for error correction. And then we have just closed a Series B round for $60 million with investors like Venrock and Innovation Endeavors, which is Eric Schmidt. So we have blue chip investors that are very impressive, and we have quite a bit of funding from which to do our development with. Now, currently, our company has 50 scientists. We are adding more every day. And thank you, Austin, in the announcements for mentioning that we're hiring. So please always check our website because we have a lot of positions open. We're in the midst of a huge expansion. We have our original system, which is a beta test system, currently in test by a number of customers, as well as we are building commercial devices in a new facility. So there's a lot going on at our company, and we're very excited about the progress we're making.
All right, so I'll jump in here. Many people think of quantum computing as a journey or a marathon, and we see the same thing, that we went through some phases earlier where systems just had to prove that they could exist, and that happened. And then a series of computers have come out to show that, yes, we can get to really high fidelity numbers and start to show quantum error correction in principle. And moving on to a phase where systems scale up, that the resources, the compute resources increase, then that opens up opportunities to explore applications and eventually hitting on those killer apps that really provide value for customers. And we see ourselves in that phase of moving from scaled systems into applications. And so I want to talk a little bit about our technology and why we're able to scale and what benefits that's going to bring. So I'll start with the idea that we're using neutral atoms. And what that means is we're encoding our qubits in the nuclear spin of alkaline earth and earth-like metals. So these are special in that their outer electron shell has 2 electrons and it's a closed shell. And that closed shell provides protections to the nucleus. So magnetic field interference or other kinds of environmental perturbations are avoided with that shell. And that is one of the secrets of how we're able to get these very long coherence times that Denise mentioned. The very high level of it is that we use optical tweezers to trap atoms in an array, and we use laser pulses to interact with them. And so I'm going to go into some detail on this operation. So 3 phases to realizing a quantum computer with neutral atoms. First is there's a involved preparation phase of getting all the atoms into the traps and lined up in the grid, ready to do operations. Then there's actually executing the quantum gates, single and 2 qubit gates, and then getting a readout from final answer. What are the zeros and ones? So I'm going to walk through each of these steps. So first step is we've got to get some atoms. So we take a source of a tiny little amount of strontium. We heat that up in an ultra high vacuum system. The atoms come spewing out at very high speed, and we use magnetic field and lasers to progressively slow these down. And so at some point you interchangeably use the words slowing down and cooling. Essentially, we're stopping the motion of these atoms. And so we bring them down to about 4 microkelvin. And this is not cryogenically doing it with an environment, but actually just slowing their momentum with laser pulses. So once we have that cloud, we have a reservoir that we can then use to fill the array in a later step. So the core principle that we use is optical tweezers. And the idea of tweezers is that we focus a laser beam down to a very fine point. And that fine point induces a dipole moment in the atom. And so the atom actually just gets stuck inside of this laser beam. So the nice part is, compared to other technologies like trapped ions use actual physical electrodes to create an electric field to hold the atom. In this case, we're just using light. We form it with light. And that laser light is much easier to arrange different trap configurations. There's not a lot of manufacturing to do. And so there's a lot of benefits, and this does lead to the scalability that we'll talk about later. So we use a single laser source and we split it apart into many other smaller lasers that then focus down. So you can see here there's an array of laser optical tweezers, and that's all coming from a single laser source. And we then have a grid, and that cloud of cold atoms then is allowed to form into this grid. And from random statistical trapping, it holds about 50%. 50% have an atom in it, 50% don't. So we're not quite ready at that stage. So the next phase is to actually organize these atoms and fill up our formal grid. And so what we use is a dynamic tweezer. So in addition to the traps that are stable and non-moving, we use a laser that is directionally controlled. So we can actually grab a hold of an individual atom and move it to where we want it to be. And this is cleverly done with, we take a single snapshot of that 50% full, we see where the atoms are, we calculate what's the most efficient way to fill the grid, and we use that algorithm to then fill up that grid. Then we are ready to start doing some circuits. And so circuits are either single qubit gates or 2 qubit gates. So for our single qubit gates, we use timed laser pulses, and we can do those kinds of operations across the array. So each atom, each qubit can have a single qubit gate done in an addressable way, but we also have the benefit of being able to do entire rows in parallel. And so parallel operations are really just a speed up so that you can do more things at the same time. 2 qubit gates are where the interesting interaction happens. So in our array, our atoms are spaced at about 4 microns apart. So in a normal case, they're relatively far apart from each other. They don't really sense each other. There's no interaction there. But what we do for the 2 qubit gates is to excite them into what's called a Rydberg state, where they actually have a radius of interaction. So that electron moves to a higher energy level, and then it can interact with the surrounding atoms. So we do an 8-to-1 connectivity. You can kind of see the geometric arrangement there. And it's through that Rydberg interaction that the 2 qubit gate happens. We can also have multiple 2 qubit gates across the array. So you can imagine doing it, there's a trade-off here between that connectivity and how many parallel operations you have. This is something we're still studying. So we've chosen an 8-to-1 connectivity, but in the future, we may consider doing higher connectivity and fewer parallel operations. Now, to get the results readout, we do a special trick called shelving, where we essentially hide the atoms that are in one state and read out the others. And so this is something that we've written an archive paper about. And through that technique, we do a camera-based readout. We have a camera that can see the either zeros or ones that are fluorescing and measure out the results. So there's several factors here that we're continuing to improve. So one of those is to move to larger qubit counts. So that involves making the array larger. So with our 100 qubit system, it's a 10 by 10, but you can imagine moving to say on order of 1,000 qubits, and where you'd have 32 by 32 or even larger dimensions in 2D. At some point, then there's also the possibility of going to multiple layers of grids, so into a 3D space. For fidelity, we're doing some changes of atoms. We will change out of using strontium to use a different atom. That'll help us get higher fidelity and also faster gates. And we'll continue to enhance the coherence time by improving the magnetic shielding and some of the laser characteristics, low noise lasers. Another area of improvement is in the control circuitry. So we do highly customized control circuitry. There's a lot, you can imagine, a lot going on in terms of controlling all of the pieces that need to come together. And we have a team of 10 people actually who design custom built electronics for that. So from a roadmap point of view, we have this 100 qubit prototype, and that's something that we're using with partners and early customers to explore in the coming year. And then we will talk about later next year launching a system that is more on order of 1,000 qubits. And then we'll continue to iterate on a relatively fast cadence with something new coming out every year. Software-wise, we have focused on those platforms that are most popular. So you could see from some of the statistics there from libraries.o, which ones we see as being most prevalent in terms of people using them and contributing to them. And so Qiskit and Circa are our first interface options. And we'll also be developing an OpenQASM API so that people can interact with other software platforms. And there are a number of applications that customers and partners are exploring with us. You can see some of them here. There is a surprising fact that almost any industry you can think of takes advantage of those areas that quantum can be good at. So it's optimization problems, acceleration of machine learning, or chemical molecular simulation. A lot of different applications there and a lot of explorations. So in summary of this portion, we're developing this scalable technology. As we scale up, the atoms are so small that we can actually get into the millions of qubits within still a cubic millimeter. So much of the hardware that we'll use will stay the same, and just kind of scaling up the inside with more atoms. We have a large experienced team, which, as Denise mentioned, we hope that people will reach out and explore possibilities of joining, and continue to watch as we launch new systems in the coming year. I'll hand it back to you, Denise.
Thank you, Dustin. I did want to also mention to the group an organization called Women in Quantum, and it's something I started a couple years ago, and it has gained huge momentum in the past couple of years. If we go to the next slide, I'm going to go through those pretty quickly. It all started with people calling and asking for advice for career coaching. And because there's a noticeable lack of women in quantum, we felt that a community was important to promote women in the industry and also to help women get careers in the quantum industry. Now, what we've done on the next slide is we've provided a stage and a space for the global quantum computing community to learn about a lot of the work that women are doing. And what I want to point out is that this is an organization that includes men and women, but it generally highlights the work that women are doing. But part of what we offer is a mentoring program. And that's what I wanted to mention to you all today on the next slide, that we have a mentoring program. It's sponsored by Keysight, and it's a enterprise software program that takes people that want to be mentored or mentees, so mentors and mentees, sorry, and it matches you with different people. And so you can have free mentoring and coaching in quantum computing. What's really amazing is that we have so many people that support being a mentor, from places like MIT. Will Oliver of MIT is a mentor, University of Colorado, Zapata, QCware, INQ, Q Control. There are a lot of companies that have really latched on to the mentoring part of this program and are available to you as a resource for developing your career in quantum computing. So I did want to mention this to you, that if any of you are interested, and you don't have to be a woman to apply, there is a link at the bottom of the screen, and you can sign up to join this program at no charge and hopefully get connected with one of the great mentors that we have. And there's just a ton of them. So I thought that would be a nice resource to point out to everybody on the call if they wanted to take advantage of it. So that concludes our remarks. Are there any questions?
Yeah, thank you so much, Denise. Really appreciate the resources.
Oh, wait,
yeah.
one more thing. I did put together a resource slide that for people on the call, if you want to look for some resources, these are some of what I recommend. And the interview with Carl Williams from NIST is coming up on Quantum World Detangled. So you'll see it on LinkedIn, and I really recommend that you watch that. All right, Austin, sorry about that.
Yeah, no, that's great. And actually, if you don't mind emailing me some of those resources, I can put those out on our Meetup page so that everyone can easily get a hold of them.
Great, happy to do that.
Thanks, Denise. Yeah, so we'll go into the question section. Yeah, if you guys have any questions, go ahead.
Yeah, I have one question, Chris Papakristo. Basically, I didn't understand one thing about the correspondence between atoms and qubits. When you form 1 qubit gates, I got that, but when you start doing 2 qubit gates, you had this, I guess, little array there, 8 kind of connectivities. So how do the atoms correspond to qubits when you have 2 qubit gates? I didn't understand that very well.
Yeah, so the qubits are formed from the nuclear spin. So there's energy levels of the atoms, and that ground state has 2 levels. Well, it has actually, strontium has more than 2 levels, but we only use 2 of those levels. The 2 qubit gate is achieved by putting a laser that is just slightly detuned enough to, in certain cases, raise it to an energy level that would correspond to a Rydberg state, in certain cases not. It gets a little complex. That's why the slide abstracted away some of that detail. But in essence, it acts like think of like a transistor where you have a control bit where it's, if this is a 0, do one thing, and if it's a 1, do another. Same sort of thing happens with the Rydberg state. So in certain cases, if a qubit that is having that gate is, take it as simplified as a 1, then it will have a certain reaction to that. And so that's the basic building block of a C0 gate, which is essentially, if you can form a C0 gate, you can form every other quantum gate. Hope that at least directionally answers your question. I could point you to some academic papers to
yeah, maybe that would help if you put a link.
Sure.
Yeah. Thank you.
Hey, Justin, this is Pathikrit Mukherjee again. I have a question for you. So you guys are doing so advanced technology to bring down the atom to a ground state almost, right? Which we see probably for Bose-Einstein condensate and stuff like that as as well. Do you have any plan in future to probably build a division for photonic computation as well? I mean, photonic
So at this point, we're
computers,
not.
because the reason what
Go ahead.
I'm sorry, I'll just take one more line. So I mean, in terms of expenses, right? It probably looks to us on a very outside world that photonic might be the cheapest one in future. So yeah, and probably generating a multi-qubit system would be much easier because we have a lot of technology already available for lasers. Yeah, that's all my question. Thank you.
So I think there are a lot of new technologies. Well, I should say technologies that people have thought about for a while. You know, neutral atom technology has been decades in the making, some of the fundamentals for it. But each of these new systems are kind of emerging as, you know, possible ways to look at it. Photonics has some merit. In our view, it's going to be more about proving every step of the way how we can scale up, you know, making a claim that you scale very easily, that it's kind of the answer to everything. It's a bold claim to make. And it's our plan to show 100, 1000 and on up to larger and larger numbers of qubits. Photonics has its challenges and they have many things yet to prove out. Could it be very interesting? Could it be very scalable? Maybe. We'll be interested to see. For now, we're focused on neutral atoms.
Okay, and any way you guys are offering like to access your quantum computers through cloud or something?
So right now we're working with select partners to do some interactions in this early stage, and we'll have it more commercially available next year.
And no free version as of now yet, right?
That's right.
Okay. I'll probably follow up your webpage to check if you guys release any free version for people like us, because 100 qubit is a big thing. Right now, IBM free version gives us only about like 5 qubits right now, and any other qubit, I mean, any other technology you want to access there, either through Azure or even AWS, there is a cost and budgeting stuff like that, and it's pretty expensive. I was like thinking it might be cheap, but at the end of the day, you might spend like $500 at the end of the month to just run few of your circuit calls. And so I was pretty interested, like when you said 100 qubit, and if it's up on the offer, then we can in future probably try something over there. And you also mentioned, if I'm not wrong, that it's very Qiskit friendly at this point, right?
Yes, okay. we have a Qiskit bridge. Yeah, so if you're developing in Qiskit, that'd be fine. I would point you to a couple resources that there are multiple, I would call them grant programs through Microsoft Quantum Azure, through AWS Bracket, through Oak Ridge National Labs. Essentially, you submit a proposal. You say, here's what I'm planning to do with the time on systems, and make a request, and they selectively will grant time with them funding the access to the hardware. So essentially, if they deem it worthy, you can access some free time on hardware. That's not particularly to Atom, that's to anybody on their platforms.
And I just sent you that information on LinkedIn. So check your LinkedIn messages and you can see about it's called a research credits program.
Okay, thank you very much. I didn't know about it.
That's why these meetups are so great. We get to tell each other all the secrets that are out there.
Yeah.
All right. Does anybody else have any questions?
So there's a question on the mentoring program, and we've just kicked off one tier. We're going to do another tranche in mid-March. So if you sign up now, you'll get included in the next round.
Awesome.
I was wondering about the, you mentioned that you have to slow these atoms down to, you put a temperature on them, but you said it wasn't like refrigerated. So are these, I don't want to call them a chip, but whatever they are, this array of atoms, is this just sitting in a room without cryostat or anything like that?
It's sitting in an ultra high vacuum chamber. So it's a, I guess, like stainless steel chamber with windows on it, and the lasers come in through the windows. But there is it's evacuated. So there's just nothing in there except these atoms that we have are holding with the optical traps. There has been work looking at making that chamber also cryogenic. If you cool that down, your vacuum becomes better. So fewer stray atoms of gas molecules to bang into your atoms of interest and knock them out of place. So it works not at cryogenic temperatures, but cryogenics can sometimes help for other reasons.
It seems like it would be, I don't want to say easy to scale up, but at least in my brain, it seems like you could put a laser in front of every one of these rows of atoms. You said you did the 1 qubits in parallel. If you're doing a 1 qubit gate on an entire row, I assume you mean you could do a different rotation of every qubit in the row, but you do it all at the same time?
Right, that's exactly right.
But what is the difficulty of making that 100 by 100 or 1,000 by 1,000? Or
well, one of the
just
challenges,
laser in front of every row and then a laser, in front of every one of them to do the 2 qubit gates.
So I sometimes get in trouble because I want to say the same thing. It's easy to scale up. The scientists take a different route. Like, come on, it's not that easy. There's some things that we got to do. There's engineering challenges to it. So one of the things is, as I had mentioned, that you use one laser to create all of those traps. So you're taking the power of a single laser and dividing it up into individual traps. So for some amount of scaling, you could just turn your power knob up on your laser and have more traps that you spread across. And I say that kind of lightly. The noise characteristics of the laser matter quite a bit. And so just having a higher power laser is not as straightforward as it sounds. But we don't see that as necessarily scaling that well. So we're doing some other clever things with optical design to be able to enhance those traps without having to increase the laser power so much. So there are challenges like that in how to get that scaled up. And then
Does
also
the grid have to use exactly one laser? Can't use 100 lasers? Or
it for various reasons, it's much preferred to use a single laser because of the characteristics and phase and other types of things.
There always seems to be a catch with quantum computers.
There's catch after catch after catch, for sure.
Catch 2 to the 22, as I like to say.
Yeah, exactly.
Okay, we are at 7:20. I think that is, we're actually ending a little bit early. But I just wanted to post an event survey in the chat. You can just leave feedback, or if there's any topics or anything that you guys are interested in hearing, you can let us know. I want to thank our speakers today. Mark, Justin, Denise, thank you so much for your presentations and just sharing the information and the progress you guys are making at your companies. It's really exciting for all of us to see, and just fascinating technology. And I see people are clapping in the clapping in the chat. With that, we will be posting this recording on YouTube in the near future. I'll send out a link to you guys, Justin, Mark, and Denise. But with that, we're hoping that later this year we can actually have some of these meetings live. But I just want to thank you all, and thank the audience. Thank you guys for joining and for your great questions. And I think with that, we'll call it a wrap.